presented as a public service by United Steel.
These are the deep, imaginative eyes that look for tomorrow. This is the active, inquiring mind in which the barriers of the future do not seem insurmountable. These are the trained hands that may push back the horizons of service performed for man by steel. From all over the country they come, a physicist from California, a ceramic engineer from Ohio, a physical chemist from Massachusetts, a metallurgist from Michigan, an electronics engineer from Georgia.
What was the coefficient of expansion at 1500 degrees?
Hardness, 320 Brinell. Creep after 10,000 hours at 1500 Fahrenheit was 1%.
No longer is research the quest of individual men, coordinated efforts of many brilliant minds. 15 miles east of Pittsburgh, in Monroeville, Pennsylvania, a new neighbor has built a campus for research, where inquiring minds seek the future horizons of steel. This is the United States Steel Research Center. On every hand, there is evidence of the accomplishments of steel science. Automobiles whose fenders and hardtops bear witness that research could and did develop a steel that could take the punishing stamping process, indeed, with an increase in strength, and the buildings themselves. There was a time when architects wished for the strength and trim appearance of steel for building exteriors. But steel, unprotected, could corrode, until research found the answer in stainless steel. It was not too long ago when much of the country's research was performed in makeshift home laboratories, and invention flourished in the attics and sheds of individual inventors like Bell and Edison. Now more than 2/3 of the nation's research and development is conducted by American industry. Where once the struggling researcher had to spend many preliminary hours to improvise the equipment for his experiments, now the finest facilities are at his elbow. Typical of facilities, many of which have been developed in the research center, is this apparatus used in the study of surface films.
I often say that when you can measure what you are speaking about, you know something about it. But when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely advanced to the stage of science, whatever the matter may be.
Thus, many years ago, Lord Kelvin recognized one of the most important factors in the approach to research, the development of accurate measurement. Many of the tools of measurement are produced in intricate designs in the center's own glass-blowing department. Some instruments are so minute that they are formed on a microforge. Precision tools whose formation can be observed properly only under a microscope. Sometimes the hand is too fast for the eye at the microscope, and much too shaky. So a unique micro-manipulator has been designed which reduces manual movement 50 to 2,500 times. This is an X-ray microanalyzer in which an electron beam can be concentrated on a selected spot about 1/10,000,000th of a square inch. This excites the atoms to emit characteristic X-rays, thus revealing the composition of the spot. A beta ray gauge is used to measure the thickness of metallic coatings. Caution is exercised in the presence of radioactive materials, which are finding increasing use in modern metallurgical research. One of the simplest means of characterizing the condition of a piece of structure itself. This micro-hardness tester, designed and built at the Research Center, combines a sensitive loading mechanism with a built-in microscope to select the spot to be tested and to make the micro-hardness measurements. This is the emission spectrograph. It is an optical instrument used to determine the chemical composition of steels, refractories, slags, ores, and other materials used in the steel industry. As a result of continued research, the accuracy, speed, sensitivity, and scope of spectrographic methods are constantly being improved. The photographic record of the emission spectrograph is today as revealing to the metallurgist as is the X-ray to the surgeon.
Finished the analysis on that heat I gave you, Joe?
That's it.
Is that the vanadium?
Right.
How's it seem?
Good. All falls in specifications.
How were the chrome, nickel, moly?
Very good.
But these are the means, not the end. For the end, as well as the beginning, lies in the creative, restless imagination of men who have devoted their lives to the solving of scientific mysteries.
Hello. Hello, Ed. How'd you like to see some evidence that Bob and I have here on how those coarse bainite structures form in low alloy steels around 900?
Fine, fine. That's what you were telling us about last week.
We find the transformations. In the first stage, a coarsely acicular constituent, somewhat resembling proeutectoid ferrite, forms.
Just about as you suspected, Bob.
Then, much later, a second constituent begins to develop, and this has an appearance something like extremely fine pearlite.
We've got some electron micros here that confirm this rather nicely. You see, here's the coarse ferrite-rich bainite that comes out first, and then the fine pearlite that follows in the second stage. Now, of course, in the optical microscope, you can't resolve this pearlite, but here, 20,000X in the electron micros, you can see the laminations pretty clearly.
Well, it was long ago that we felt that the structure would prove to be lamellar.
That's right, that's right. Would you like
Dr.
to have-
Edgar C. Bain once described the spirit that motivates this constant search as a noble discontent with things as they are.
We've just been showing Ed some of those electron micros that were taken last week. Do you remember those?
Oh, that's fine. But there's one problem that should be solved. And that's how to get better coffee out of these machines.
You're right.
We can start something there.
The camaraderie of science touches on many subjects. It may be thermodynamics or what happened to the Pittsburgh Pirates. But the conversation is always animated. And there's many a doodle or curve or equation on the paper napkins at lunchtime. Every problem solved produces many more in its place, and the areas of research are unlimited. Among the major problems are the more efficient use of natural resources or scarce materials, the conversion of what used to be waste and pollution into useful, marketable chemical products, and always the constant inquiry into the basic structure of steel itself. For steel is not just steel. There are many, many kinds of steel now in use, and many under development. Among the 90-odd naturally occurring elements, there are around 26 common metallic elements that in principle might be alloyed with iron to form steels with a wide variety of characteristics. There are only 26 letters in the alphabet, but combined in different forms, they produce hundreds of thousands of words. And yet there is one right word for the time and place. So too, there's a right steel for the time and place. In probing the more efficient use of natural resources and to improve further the efficiency of steel-making facilities, research scientists often work with models simulating operating conditions. Here they're examining the movement of a column of granular solids against an airstream in the study of potential improvements in blast furnace design and operation. Many plastic models are specially designed and built in miniature in order to analyze the patterns of turbulence, for example, in the flow of open hearth gases. Back eddies had long been suspected, but now such inefficiencies can be pinpointed with greater accuracy. Iron ore is one of the great natural resources of the earth. Yet, there's an eventual limit to the availability of firm, high-grade, coarsely sized iron ore for blast furnace use. Some of it is too low in iron content and must be crushed and concentrated. Some of it is too fine and must be compacted, or as they say, agglomerated. A major area of research is now devoted to learning how to turn lower-grade iron ores into high-grade, well-compacted material for blast furnace use. At the top of this small pilot sintering plant at the research center is a rotating shallow pan which is used to pelletize fine ores. With the right water content, and perhaps with suitable binders added, the device actually tumbles fine ore into little balls or pellets. Thus compacted, the material is baked until it clinkers, much like the familiar clinker in a coal furnace. The result is a strong, conditioned material that reacts with great efficiency in the blast furnace. Blast furnaces like this diet. While research is testing how most efficiently to change materials with the aid of heat, it is also testing how to perfect materials that will resist heat. This is a brick, a seemingly simple brick, and yet it represents one of the largest single items among the auxiliary materials purchased in the making of steel. Whatever can be learned that will increase the useful life of a fire brick can mean millions in the operating budget of U.S. Steel. For there is enough brick in the lining of one open hearth furnace to build 75 six-room houses. And some of these bricks cost nearly $1 apiece. How resistant can a brick be made to withstand temperatures as high as 3,000 degrees or higher? How often can it survive heating and cooling and the attendant expansion and contraction? In so-called spalling tests, brick samples are terrifically heated one moment and then abruptly given a water and air spray. Peculiarly enough, while the philosophy of research is highly constructive, much of the application is destructive. The research technician is forever breaking things, the purpose being to find the breaking point, the melting point, the point of ultimate failure, and then to find out why. So the temperature is raised ever higher. The test is much more severe than that of any actual operation. First, they develop a brick which they believe will do the job. Then they do their best to break it down. The result is not alone a collapsed brick, it's a knowledge of how far we've gone and how far we can yet go in the containment and application of intense heat. Coal is black, you might say, but not to the scientist who sees in the microscope minute layers of vegetation sedimented millions of years ago. Studying the content of various coals, research pursues how best to blend coals for coking for the recovery of coal chemicals in the coking process. For the gases that used to escape from beehive ovens have now produced a whole new chemical world. First it was tars, naphthalene, and creosote. Then solvents and the glittering galaxy of dyes and plastics. So effective has been this field of research and development that a significantly increased part of steel's future business may well lie in the production of coal chemicals extracted from gases produced in the making of metallurgical coke by the distillation of coal. You are here taking a seemingly microscopic look at the destructive head and jaws of a limnolia. Like other marine animals, the teredo and the pholad, it destroys wood, voraciously gnawing endless paths through the toughest of wood fibers and costing the country a fortune in damage. But they shy away from creosote and other coal tar derivatives. So this peculiar study is just another battleground of U.S. steel research. This is tin. Tin for plating. Tin is expensive, scarce, and the presently known areas of supply might be cut off from our country. Although the so-called tin can is more than 99% steel, much research has been devoted to more efficient use of this other element in combination with steel, and in some cases to the entire elimination of tin in the production of certain cans and containers which used to require this metal. Fortunately, U.S. steel research had developed the electrolytic process of coating steel with tin before World War II, so that by the time our tin supply lines were threatened, a method had been found to reduce the consumption of tin for plating by nearly 50%. This research goes right into the kitchen. Into the kitchen, that is, of U.S. Steel's Tinplate Research Division. Different weights, different coatings, and various lacquers applied to tin plate are tested here. More and more lacquers and other coatings are being developed and tested against the day when the tin can might become completely and perhaps more beneficially the steel can, conserving scarce tin for more vital uses. Progress in canning research is already manifest in the fact that many products, dry materials, paints, and less active food products need no longer be preserved in tin plate and are now packaged economically and durably in steel that is chemically treated or lacquered or both. Storage in hot rooms where the temperature is maintained at 100 degrees helps to accelerate the testing. Porcelain enamel is low-melting glass. Being a glass, it has great resistance to corrosion and offers, in addition to the advantages of its surface, the warmth and decorative charm of a wide range of color. The research job here is how to prepare steels for more efficient bonding with enamel to avoid pitting, chipping, and other faults that have presented problems to the manufacturer and to the housewife. One of the promising new developments has to do with a method of pre-coating steel sheets to improve the resistance of subsequently applied enamels to cracking and chipping. In a torsion test which twists the enameled sheet, it may be seen that there is noticeable distortion before the enamel cracks off. In combining alloying elements with steel, the scientist is constantly on the alert to eliminate impurities. For example, the presence of hydrogen in certain steels, even though only 5 parts in a million, can have significant effect. So penetrating is the search for such elements that in some studies steel is both melted and cast in a vacuum, as in this 2-pound vacuum furnace. Whether or not steel in 100-ton batches will be commercially melted in vacuum, extensive research in the small vessels is productive of much beneficial information. And already the casting of steel in vacuum has been achieved in large quantities, with ingots up to 80 tons being cast in controlled vacuum, with the result that hydrogen has been reduced to a level of about 1 part in a million. It's a long way from an 80-ton ingot to one that can be held in the hollow of one's hand. Yet here is perhaps the birthplace of better steels for tomorrow. The 2-pound furnace screens the compositions for the next step. In this case, a 300-pound furnace in which steel is both melted and cast in a vacuum. In developing new steels, the research people have built up a philosophy of alloying which enables them to forecast with amazing accuracy the properties which will result from new alloy compositions, as well as the changes in the character of steel which are produced in the course of heat treatment or by manipulation such as forging or rolling. But from time to time, the unexpected is observed, and a better theory, and perhaps a new steel, is the special reward of the research. A classic demonstration illustrates the changed character that heat and manipulation impart to steel. In a testing machine, two pieces of the same steel are fixed. The missile-shaped piece at the top has been hardened by heating and quenching. The disc-shaped plate at the bottom has been softened through heat treatment. Both are the same steel, yet one pierces the other with ease. The mechanical testing of steel subjects it to every kind of engineering torture. It may be fractured with standardized and carefully measured physical force, or it's bent and rebent hundreds of thousands of times. It's pulled apart by thousands of pounds of tension, always probing the breaking point. It's machined with microscopic examination of results. One way or another, this intense scrutiny assures us that the answers will be found, that steel can and will meet the demands of tomorrow. It takes a combination of curiosity, disciplined imagination, and fine discrimination to guide the study of steel performance in miniature and to project this experience into engines, cables, pressure vessels, or structures of ever-increasing capacity. Some of the most spectacular problems of the jet age are those that confront the steel metallurgist. For progress in this age of speed hinges on our ability to create steels which remain strong at ever higher temperatures. Here in what is known as the creep rupture laboratory, the strength of steel is measured under conditions of tension and time and heat. 1,000 hours of stress under conditions of high temperatures and tension. The steel under stress is encased in small electric furnaces, which if cut away would look like this, while the heated steel is subjected to measured tensile pull, anticipating the requirements of supersonic air flight structures. Some research testing assumes highly realistic proportions, as does this dynamometer, a giant machine especially designed by the Research Center to test railroad wheels. It can produce a brake load far in excess of that on each wheel of a 100-car train going 100 miles an hour. What happens when the engineer applies the brakes at high speed? What happens to the surface of wheel and brake shoe? What happens in the heat transfer and expansion of steel? Now the problems can be attacked with extreme thoroughness, seeking steel and treatment to meet the challenges of greater loads and greater speeds. Another objective, and a product of research as important as any new steel, involves the development of men, continuing their training in science and in technological processes. Here, the objectives are the stimulation and refinement of curiosity, and strangely enough, the cultivation of restlessness. For the very nature of research is such that its future cannot be predicted. If we are completely satisfied, or if we contentedly get along with compromise, research may hold no interest for us. The essence of research is a restless sense, not dissatisfaction with what has been accomplished, for of that research is proud, but a sense of incompletion, of perfection not yet attained in knowledge and in standards of living as well. These are men who have indeed a noble discontent with they are. Theirs is a restlessness that steel research would nurture, for without that restless urge, our progress would cease.